Hello, my name is Hania Habib and my student ID is 23352505920. And today's date is the 18th of March. And in this video, I will explain my OMNET++ Computer Networks Laboratory project, which will include Step 4, Step 5A, Step 5B, Step 6A, and Step 6B, along with the differences in routing behavior. So here is the OMNET interface. So this project is based on simulating a network using OMNET++, where we can analyze how routing tables are formed and how packets travel between nodes. So here we use different configurations to observe, like automatic routing, manual routing, and metric-based routing. So each step modifies how routing decisions are made. So this is the step 4, and it's like step 4 configuration in OMNET pp.ini. And here in step 4, the fully automatic stated routing is implemented. So here the configurator module automatically generates routing tables based on the network topology. So this means that no manual routes are defined and the shortest path routing is automatically calculated. So here I show how the routing table is formed. So the routing table is formed using the configurator, and each entry contains destination network, netmask, gateway, interface. And what it does is that netmask defines the size of the network, gateway is the next hop router, and the interface is the outgoing port, which is used to send packets. So here in the step 4, the shortest path is determined automatically, which is topology. The configurator is using algorithms based on topology and link connections to find a path with minimum cost, which usually is based on hop count. So the packets are following the most efficient route between source and destination. Now here it shows the packet flow, so we can see the packet flow in the simulation. The packets are generated using Ping app and forwarded through routers. So the arrows show the selected shortest path, and the logs below confirm successful transmission and routing decisions. Now this is the step 5A configuration. So in step 5A, automatic routing is disabled and we manually define routing in entries. So this means that we explicitly specify the destination, the gateway, and the interface. So we can see that what it achieves is that this allows the full control over routing behavior. So instead of relying on automatic shortest path, we define exactly how the packets should travel. So this is useful in real networks where administrators control routing policies. So this is the XML file. So the difference from step 4 is step 4 is automatic routing and step 5A is the manual routing. So the routing decisions are no longer dynamic, but they are predefined. Now here it shows the manual routing like multiple routes. So this is the step 5B configuration. So in step 5B, we extend manual routing by defining routes for multiple hosts. So it means that more routing entries and more detailed control over different destinations. So the difference from step 5A is that step 5A defines routing for a specific host, while step 5B defines routing for a set of hosts. So step 5B is more scalable and closer to real-world routing tables. Now this is the step 6A, which is the 6A configuration. So in step 6A, routing is based on metrics, specifically data rate. So instead of just short path, routing considers link bandwidth. So the higher data rate links are preferred because they can transmit faster. Now here the fastest path is selected, and this is different from the shortest path because the shortest path has fewer hops and the fastest path has higher bandwidth links. So the routing decisions are based on performance, not just distance, as we can see over here. So here in step 6B configuration, we manually assign link cost values. So each link is given a cost and routing selects the path with lowest total cost. And here it shows the cost impact. So some links are assigned higher or infinite cost, which makes them less preferable or completely avoided. So routing is forced to choose alternative paths, like this, like XML cost or infinite. So the difference from step 6a is that step 6a uses automatic metric based on data rate, while step 6b uses manually defined cost. So step 6b gives more control over path selection. So here is the INI showing extents and the inheritance. The inheritance is used in Omnet++, as we know, which uses the extends keyword. So for example, step 5 extends step 4, so which means that step 5 inherits all properties of step 4, and it only modifies specific parameters. So this actually reduces code repetition and improves modular design. So the network concepts is like net mask, which defines which part of an IP address belongs to the network. For example, for example, if we have 255.255.255.0, it means that first 24 bits are network park. And in the same way, like gateway is the next hop router used to forward packets outside the local network. And interface is the physical or logical port through which packets are sent or received. So here we can see that the simulation is working. So the simulation runs using Omnet++ runtime environment. So the packets are generated, routed, and visualized in real time. And we can see the visualization, which is the packet movement. So the visualization helps us understand routing behavior. We can see the packet flow, the path selection, and routing decisions. And we can see the authorization, that configuration is controlled through omnetpp.ini and XML files, which defines that the routing rules, application behavior, and simulation parameters. So when building a network, we must consider efficient routing, avoiding congestion, proper metric selection, and scalability, because incorrect routing configuration can lead to inefficient and failed communication. So finally, in conclusion, this project shows that how routing tables are found, and how shortest and fastest paths are selected, and how routing behaviors change with configuration. So it helps in understanding the theoretical and practical aspects of computer networks.